Hello and welcome to session 3 on organic chemistry. In this session, I'm going to get you to understand how to name and draw straight chain alkanes and alkenes with only 8 carbon atoms in their chains. And we'll also look at how to use the general formula to identify alkanes and alkenes given a molecular formula. Now, this is where we're going to start defining some of these words so that you understand them much clearer. Like we're saying earlier in the first session, I mentioned the word alkane, alkene, cycloalkene, and aromatics. We're going to be looking at this session by session so that you understand these much better. Let's start off here. At the start, I told you that I can have carbon atoms bonding in a chain, and when this chain of carbon atoms forms, right, we can have single bonds throughout the chain between the carbons, okay? When we're talking of the single or double bond, which I'm going to refer to earlier, we're only looking at these blue ones, okay? I'll distinguish this and use blue to distinguish or differentiate them. So if you look, you're given a formula of a hydrocarbon and you look at the bonds that are forming between the carbons and they're all single bonds, there is no double bond, then that's what we call an alkane. So how do we define an alkane? An alkane is a hydrocarbon that has got single bonds between carbon atoms in the chain all the way through. Okay, but if you see a hydrocarbon that looks something like this here, okay, I'm going to put lines here to represent hydrogen. I'm going to tell you something here as well, guys. It's really important that as we move on from this point, when you draw these structures, make sure you physically count the bonds around each carbon to make sure that a carbon has got 4 bonds. I can't tell you how many times I just see students doing such a thing, whereby now if you look at this carbon here, how many bonds does it have? This carbon now has how many bonds? 1, 2, 3, 4, 5. There is no way carbon can form 5 bonds. That's why I did not add this bond here. So make sure you physically count when you're starting. It doesn't come naturally. When you're starting, you need to physically count the number of bonds around each carbon to make sure you've got the right number. Right, I'll put this in red to differentiate that from the blue, which are the hydrogens. Right, this one here, if you look at 1 and 2, right, there is a difference here. At this point, I've got a double bond at the start of the chain. This double bond can be anywhere along the chain. But as long as I've got one double bond, at least one double bond in a chain of carbon atoms, then that will be an alkene. The most important thing, guys, there is the double bond must be between carbon atoms for it to be an alkene. And you need only one in the chain, at least one for it to qualify to be an alkene. For alkanes, there is no double bonds. It's all single bonds between the carbons throughout the chain. So it's really important that we know that, because when we name, it's really important. And to identify them, it's also important that you know that difference. Let's move on. So to get you to have something to write, alkenes are those hydrocarbons in which the carbon chain has single bonds throughout the chain, or that is, the single bonds must be between carbon atoms, like this one here. This is an example. I've got an example of 3 alkanes here. If we look at it this way, let's look at the names. They all end in what? In ane. So given a name, anything that ends in ane, it's an alkane. Okay, this here is what we call the suffix of the name. I'm going to use these words quite a lot. So all alkanes, if you are not given a formula like that, if you are not given a structural formula like that, you can identify that by the name, because they have to end with ane, right? And if you are given a structure, just look at your carbons and see that, oops, they are all single bonds between the carbon atoms, so there's no double bond. That must be an alkane. That's how we identify alkanes, right? There's another way of identifying alkanes we're going to look at when we look at the general formula, but for this, these are the two ways you should know by now of identifying alkanes. The third way, we're going to look at it later. Let's look at the next point. For alkenes, you need at least a single bond, a double bond in the chain for it to be an alkene. And here's, I'm going to give you these examples here. Right, I've got these examples. I've got ethene, propene, and butene. As you can see, they all end in what? In. Okay, this is my suffix because it ends in. If we look at the previous slide, let's go back to the previous slide. You can see that the start of these here, because we start from here, eth, prop, is the same for the next one, which is our group of alkenes. Let's look at alkenes. Eth, prop, and but, they're just the same, right? This is what we call the prefix. So the names of these hydrocarbons, they've got a prefix and a suffix. So we're combining those together, and there's a pattern that follows. We've already seen that the suffix of all alkenes is ene. The suffix of all alkanes is ane. Now we want to look at the prefix. The prefix is actually, I'm going to preempt this. We start from, the first one is meth, eth, prop. Let's just get up to these first four. Actually, we're going to look at those in detail. The prefixes tells us the number of carbons in the chain. Meth means 1 carbon, eth means 2 carbons, prop means 3 carbons, but means 4 carbons. So that's what it is basically. The prefixes will tell you the number of carbons in the chain. For alkenes, because for alkenes we need at least a double bond. You're not going to have an alkene which has got 1 carbon. That's why we started from ethene here. We can't have an alkene with 1 carbon, because for it to be an alkene, at least we need a double bond between carbon atoms. A single carbon cannot form a double bond with itself. So basically that's the simple logic. Okay, let us move on. We're going to look at these prefixes in detail later on. Let's just carry on and look at the next part. So basically, guys, what we've looked at is the structure, the general way of identifying or differentiating between alkanes and alkenes, so that you can get something to write down. The prefix will tell you the number of carbon atoms in the chain. Like I gave you the first 4 prefixes, which is meth for 1, eth for 2, prop for 3, but for 4. You can call it but if you want, but I prefer butane, not butane. It doesn't sound right. Okay, the suffix tells you the functional group of the organic compound. So it tells you basically, like with an alkane doesn't have a specific functional group. I'm going to explain what a functional group is just in a minute. But if you look at an alkane doesn't have a specific point of difference in terms of the bonds. They are all single bonds throughout. But if I give you an alkene, you can see that, okay, I've got all single bonds throughout the carbons, but this one is unique. There's a double bond there. This is what we call a functional group, right? A functional group is that part of an organic compound that will determine its physical and chemical properties. So when an alkene reacts, or all the physical and chemical properties are usually determined by the functional group. So the suffix will tell you what type of a functional group it is. So if I've got "in," it means there's double bond. If I've got "ane," it means there are no double bonds. That's what it simply means. Right. So what is a functional group? I've already stated this one for you. it is an atom or group of atoms or a part of an organic compound that defines the structure of the family of compounds and determines the properties of the family, right? So basically, if I look at this double bond here, right, all the properties of alkenes, why they are different from alkanes, is because of this presence of the double bond. That's what it basically means. And when you study more organic compounds, you find that functional group will play an important role in distinguishing the properties and the structure. Right, now let's look at the prefixes. So we've got meth, that's 1 carbon, eth, that's 2, prop, that's 3, and but, that's 4. And there's a mnemonic for remembering this, which is monkeys eat peeled bananas. That's the mnemonic you need to remember for this, so you can use to remember these ones here. Okay, thought it would give that a stylish entry so that it will stick in your memory. So monkeys eat peeled bananas. That's how I would remember the first 4 prefixes. Okay, let's look at the remainder of the prefixes. Right, the remainder of the prefixes that we're supposed to know, for your syllabus, you're supposed to know up to 8. But I've just stretched you up to 10. It doesn't make a difference. A couple more won't do you harm. Probably some of you can do even up to 20 because it's simple logic here. So from 5 onwards, we now then originate from shapes of polygon, from names of polygons. So pent for 5, hex, they all end in A, but we truncate the A so that it makes more sense. Hept for heptagon, heptane, octane, nonane, decane. So all I do is I count the number of carbons, and if there is single bonds, it ends with ane, and if there is double bond, it ends with in. So do we have this one here? No, we don't, because we can't have an in because we've got only 1 carbon. Okay, so I did that. See if you can identify that. We don't have, this one does not exist. Not exist. Okay, so the in will start from 2 onwards. Okay, as a skill practice activity, what I want you to do, guys, is I want you to copy this table, and this table here has got 1, 2, 3, 4, 5 columns, and you need a 5-column table. You might have to turn your piece of paper or your paper or your notebook into a landscape format. You draw this table here. When you've drawn the table, I want you to name the first 8 alkanes. Okay, you complete this, and I want you to do the structure, which means you just put all the carbons in a chain. Whatever is remaining, you add the hydrogens. And I want you to do the molecular formula. I'll do the first one for you. The first one, 1 carbon, carbon 1, it's methane. And the structure will be, I have a carbon, only 1. And the carbon can form how many bonds? 4 bonds. And H, 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 H. I complete the remaining with hydrogens. And the molecular formula will be, how many carbons do I have? See, we always start with a carbon. And how many hydrogens do I have? I've got CH4. Okay. The next part is the mathematical relationship between carbon and hydrogen atoms. I've got 1 carbon and I've got 4 hydrogen, right? So basically, how do I go from 1 to 4? I can say 1 plus 1 plus 1 plus 1. But what am I doing here? There is a mathematical relationship that is apparent here. I'm taking the number of carbon, I'm saying 1 plus 2 times 1 plus 2. Okay, this is what I'm doing here. Okay, this is what I'm exactly doing here. I'm taking, if you do that, you'll find that the relationship between carbon and atoms is fulfilled by this formula that I've given you here. Okay, so what I want you to do is to list the rest, pause the video and try, and then come back to this later. Okay, I've also paused the video and I worked through the answers, and I'm sure you did the same as well. So I'm expecting you to have all the answers ready for you to check what you would have done here. Right. Just another thing I need to add here. When I wrote methane, I actually showed all the carbons, but when you're in actual sense, when you're dealing with hydrocarbons, if you just show the bonds where the hydrogens are supposed to go, that's good enough. You don't need to worry about adding the hydrogens. The most important thing is you indicate all the bonds that are needed to complete the bonding capacity of each element or of each carbon that is in the chain, and that will be good enough, because once we have this is what we call a skeleton structure, where we've got all the carbons, but the hydrogens, we don't need to add them. And these are the formula, the molecular formula for this, for all the first 8 alkanes. And if you look at the general relationship, for each hydrocarbons, it remains pretty constant. What it simply means here, what I've done is, if you take the number of carbons, right, how many carbons there are, and you double the number of carbons and add 2, that will give you the number of hydrogens all the time. That's how this formula works. So you take the number of carbons, double them, add 2, that will give you the number of hydrogens that are in the alkane. Okay, so that gives us this here, which we call the general formula. So what this general formula simply means is N represents the number of carbons, which is the prefix. So if I say heptane, N will be 7. And if I want to get the number of hydrogens in heptane, what do? I say 2 times 7 plus 2, which gives me what? 16. Okay, and I'll do the same if it was 8. That will be the same thing again. It will be Cn, which is 8, 2n plus 2, which is 8 times 2, which is 16 plus 2. That gives me 18, C8H18. So yes, there is a pattern between carbon and hydrogen, and that pattern is constant, and it gives us this general pattern, which is the formula. That's what we need to know. So this is the third way I was talking about of identifying alkanes from alkenes. So what you simply look at is this fulfilling this formula here? I might give you a molecular formula, and you should be able to tell whether it's an alkane or an alkene based on the molecular formula. Okay, I'm going to stop here and bring up another skill practice activity for this session, because I don't want this video to be more than 20 minutes. I'm going to 18 minutes right now. So I'll stop at this stage and I'll see you for the next skill practice activity, which is the same table basically, but for alkenes this time. And we want to see if we've got a pattern for alkenes. I'll see you when we look at the next skill practice activity.